Welcome back, ladies and gentlemen. In this video, we'll be talking about the conservation of momentum. Specifically, we'll be talking about conservation of momentum as it applies to both collisions and explosions. Okay, first of all, conservation laws. There are three big conservation laws that govern things in the universe. That is the conservation of mass, conservation of energy, conservation of momentum. Okay, and a conservation law just means that in any isolated or closed system, the total amount of, in our case, momentum will not change. Okay, with a formula, that means that our total momentum initially has to equal our total momentum finally. Okay, that squiggle there is the Greek letter sigma, and that means the sum of. So the sum of momentums initially is going to be equal to the sum of momentums finally. Okay, so why is this true? So Newton's laws, our first Newton law is the law of inertia, or we need an unbalanced force to change the velocity of an object. Newton's second law quantifies that, where we have a net force is equal to, will cause a mass to accelerate. And the third law is where forces come in pairs. So they come in action and reaction pairs. So in this case, a person is stepping off a boat, so they will end up moving forward as the boat moves backwards. Okay, so the conservation of momentum, really the initial equals the final. There it is with the formula. And just to show you what this looks like, this is going to be a big formula, but it's really just a bunch of MVs. And each of those MVs are momentums. In this case, we'll have momentum of our first car before the collision plus the momentum of the second car initially or before the collision is going to be equal to the total momentum of each of those cars afterwards. So it's really just adding up a bunch of momentums, and this formula that we see on the screen, that will change just depending on the different situations that we'll see. Okay, so here's a first question where we're given a bunch of information. I'm going to jump right into how I like to set up conservation of momentum questions. And that's really where I look at a situation before and after. Okay, and we just have to have our total momentum before is going to be equal to our total momentum after. So this little squiggle line is where I'm just going to imagine an equal sign being right down the middle of it. So if I start drawing out this question, my 30 kilogram mass is moving to the right of 8.0 meters per second. So I'm just going to draw my mass in a circle with the number 30 in there, representing 30 kgs. So I won't write the units every single time, but we just have to remember that we are talking kilograms. It's going to collide with a second mass of 20 kilograms. That's going to be moving at 10.0 meters per second to the left. After the collision, the 30 kilogram mass is moving at 5 meters per second to the left. What is the final velocity of the 20 kilogram mass? So we're looking for the final velocity. Now I'm going to draw my velocity to the right direction, and that's going to be important when we go into our equation. And in our equation, we're looking at so the total momentum before. So if I just add up or put in our MV, so our first momentum is going to be mass, which is 30 times the velocity of 8 plus our second mass times velocity. In this case, our velocity has to be negative 10 because this is acting to the left. Okay, on the right side, we're going to add up the momentum. So the momentum of our 30 kilogram object will be 30 times negative 5 plus the momentum of our second object, which is 20 times v. So I've left that velocity positive. When I go through and solve my math, if the number comes up negative, then I know that the object actually ends up traveling to the left. Okay, after we get this set up, this is just a big, we're just chugging out now. It's 240 minus 200 is equal to negative 150 plus 20v. Okay, if we move the 150, negative 150 over to the other side, we should end up with 190 is equal to 20v, or v, the velocity of our 20 kilogram object will end up being 9.5 meters per second. And because that number that we solved for is positive, this will be going, we know that it's going to be going to the right, because right is what we are considering our positive direction. Okay. Okay, next example. Next example is if we have a hungry to inflict pain linebacker, 135 kilogram linebacker. So there's my 135 kilogram mass running at 8 meters per second, tackles 105 kilogram running back, running at 11.5 meters per second head on. So head on means it's heading straight towards the other object. Our velocity there is 11.5. Okay, that's the before. And then afterwards, they become one big mass because we're told that the players stick together. So if they stick together, that mass is going to be a total of, well, we just add up our masses here. So 105 plus 135. So our total mass on the right side will be 240 kgs. And again, I'm going to call this velocity to the right, because that's what we're looking for. And then if we solve through this problem and we find that our velocity works out to be negative, then we know that our final velocity of these two objects will be heading to the left. Okay, so again, the squiggle line down the middle, that just indicates the separation between before our collision and after. Okay, so now if we just go through and plug and chug all of our momentums, so momentum is mass times velocity, so our first object will be 135 is the mass times 8 meters per second is the velocity. Our second object has a mass of 105. The velocity in this case has to be negative 11.5 because it is heading or directed to the left. Okay. On the right side, or after the collision, we only have one object. So our object has a mass of 240 kilograms. Our velocity is v. Okay, and after this setup, now we're just going to chug out some numbers. We should get 1080 minus 1207.5, and that's going to be equal to 240 times the velocity. Okay, if we keep working through the math here, we should end up with a velocity, a final velocity of both these masses of 0.53 meters per second. Oh, that should be a negative, so that is acting then. We know that that velocity is acting to the left. Okay. Okay, we'll look at one other example, which is an explosion. In an explosion question, if we have a 30-gram bullet that's fired from a 4-kilogram gun. So I'm going to draw my line here because this is sort of after the explosion. To start off, this $4-kilogram gun and the bullet, their total mass will be 4.0, sorry, that should be 0.03. Okay, and the velocity to start off, they're just starting off at 0. So in an explosion question, your velocity is generally 0. So sorry, this is a little messy, but all I did was figure out the total mass there of that object, which is 4.03 kilograms. Okay, so in the after situation, we've got this 4-kilogram gun. So here I'll draw this is my 4-kilogram gun. We want to know what the recoil velocity is. So this velocity, I know it's going to be going to the left. So in this case, I'm going to draw it to the left. Our bullet is going to be fired at 360 meters per second. The mass of that bullet is 30 grams. So I'm going to have to convert that into kilograms, which would be 0.03 kgs. Okay, so in this case, my initial momentum, on the left side of my equation is going to be mass times velocity, and our velocity is 0. So there is no momentum to start off. So the momentum on the right side then is going to be the mass of our gun times its velocity plus the mass of our bullet times its velocity. And now we have an equation that we can solve. Okay. So if we work through the math of this thing, we should end up with 4.0 V and plus, it works out to 10.8. Okay, if we move the 10.8 to the other side, 4.0 V. Okay, and then if we divide both sides by 4, we find that our velocity of our recoil velocity of our gun is 2.5 meters per second. And because our math works out to be negative, we know that this thing is going to be acting to the left. Okay, so I know I drew my velocity arrow here to the left. In the other questions, I drew it to the right. However you draw it, you just remember just to leave it positive. Like, don't put a negative in front of that. Let the math sort out what direction your velocity is going to be happening in. In this question, it's clear that the velocity is going to happen to the left, but for other collision problems where you have objects coming together, the direction of that velocity is not always going to be super clear. So just keep that number positive, your unknown velocity, keep that number positive, and if your math works out to be a negative number, then you know that it's happening in the, your velocity is happening in the negative direction. Okay. Okay, so your turn. So here you've got a snowball that's going to come along, and here's your snowball comes along and hits the cap off of a snowman's top hat, and the masses of both are given. Note that both of the masses are in grams, so we'll need to convert those to kilograms. So 85 grams ends up being 0.85 kgs. Okay, I'll let you convert the 135 grams to kilograms. Okay, so this is like the football tackling question where two masses become one. Okay, so see if you can work out how fast was the snowball moving before the impact. So what is the velocity of your snowball before it actually hits the top hat? Okay, answer that on your screen. Please, you can do that now. Okay, thanks, ladies and gentlemen. Please give the conservation of momentum worksheet a try. I think there are 8 questions on there. Thanks, and we'll see you again soon.